So today we're going to look at the game of Nim, and then we're going to try to write an algorithm that can play against a human opponent. So here is the rule of Nim. So Nim is just a random number of stone organized into piles, and on each turn a player can remove any number of pile from any remove any number of stones from any pile, but he cannot remove stones from different piles. And then there are two versions of the game: the normal version, in which the player who takes the last stone wins, and then the misery version, in which the player who takes the last stone loses. So the problem and challenges here is that what type of game is Nim? Is it more like tic-tac-toe or chess? Is it mathematically solved or not? So if the game is mathematically solved, then there is a winning strategy for the game. We know exactly who is going to win, and we know exactly who is going to lose, and we know exactly if a move is a winning move or a losing move. Whereas for a game like chess that is not mathematically solved, we don't know if a move is winning as a winning move or not. So the most important task here is to decide if the game of Nim is solved or not. And as it turns out, Nim is an impartial game. What impartial games are is that they the allowable move to a player depend only on the position of the game and does not depend on which of the player is playing. And for all impartial games, they are mathematically solved. All impartial games are mathematically solved. And these types of games are also classified under combinatorial game. What combinatorial games are is that first there is perfect information to both players. So for example, chess, the board position is visible to both players at any point. Whereas for poker, that is not a combinatorial game. Your opponent's hand is hidden from you, so you don't have perfect information of the game. The second rule is that there is no random factor in play. So for example, poker, every turn you draw a card, and that is a random card, and so that's a random factor. Whereas for chess or Nim, everything is perfect. It's perfectly calculated and generated. There's just nothing random. So to determine whether a position is a winning position or a losing position, in impartial game we usually use backward induction. So for example, if a game of Nim starts in the position of 4, 3, 2, that is 3 piles of 4 stones, 3 stones, and 2 stones respectively, and the terminal position is 0, 0, 0, and in normal play this is a win. In impartial game theory, we refer to this position as a P position. It means that it secures a win for the previous player. That is, the player who plays a move and arrives at this position is winning. And every position that leads into a P position is an M position. An M position means it secures a win for the next player. So if you make a move and you arrive at an M position, you're losing. And if you make a move, you arrive at a P position, you are winning here. So let's assign M position and P position to this state diagram of the game of Nim. So this is P position, M position, P position, M position, P position, M position. So according to impartial game theory, we know that the starting position is an M position. What that means is that the first player who plays in this position is guaranteed to win the game if he plays the game perfectly using the perfect winning strategy. So now we know that there is a perfect winning strategy for the game of Nim. What is this strategy? Let us first introduce the concept of Nimber arithmetic, Nim sum. Nim sum is represented by the symbol of a circle with a plus sign in the middle. How we do this operation is that we represent the number as distinct powers of 2, and then cancels out all pairs of equal powers. So for example, 13 Nim sum A, Nim sum 4, what we do is that we represent 13 as 8, 4, 1, and then we Nim sum the number together by canceling out all equal pairs of 2. All equal pairs of powers of 2. So we're left with 1. Another way to do this is using binary operation, XOR. This is the exclusive OR operation. What it does is that it returns true if and only if one of the input values is true. So for example, 1 XOR 1 is 0, and 1 XOR 0 is 1, 0 XOR 1 is 1, 0 XOR 0 is 0. So how do we name sum 5 and 7 together using this operation? First, we have to write out the decimal number in its binary form. That is, 5 is 101, 7 is 111. And then we apply the XOR operation to the numbers in the column. So 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 1 is 1. Then we get 0, 1, 0, and we convert that back to the decimal form, and we get 2. So 5 nim sum 7 is equal to 2. In Python, this symbol is represented using this thing. This is a property of the XOR operation. This is going to be very important for us to prove our winning theory later. So for the game of nim, we know that there are p positions and n positions, right? And if we analyze these p position and n position, we can see that every p position has a nim sum of 0. This has a nim sum of 0. This has a nim sum of 0. This has a nim sum of 0. And all the n positions have a nim sum of non-zero. So this has a nim sum of 1, this has a nim sum of 2, this has a nim sum of, let's quickly do it in our head, this is a nim sum of 5. So it is not 0. And all these other n positions have nim sum of non-zero. So we arrive at the conclusion that all positions with a nim sum of 0 is a losing position. Like if you need to play a move in this position, you're losing here. Whereas all the position with a non-zero nim sum is a winning position. If you are to play a move in that position, then you're winning. So for example, in this starting position, the first player to play will always lose the game because he is forced to change the game into a non-zero nim sum state, and that is always losing for him. So here comes our exciting winning strategy. So to prove our winning strategy, we're going to break our theorem into lemmas. The first lemma says that if the current nim sum of the game is 0, then the next move must change it to a non-zero nim sum. How do we prove this? Let us set S equal to the nim sum of the current position. And we know S is 0. And S can be represented as each pile nim sum with all the other piles. So pile 1 nim sum pile 2, nim sum pile 3, all the way up to pile n. And we let T be the nim sum of the game after a move is made. Because we know that after a move is made, only one of the piles is changed, because that is the rule of the game. So we know all these other piles, x1, x2, x3, are going to be the same after a move is made, except for this singular pile, and we will call this xk. And then we will let yk be the resultant pile after a move is made. And then if we apply these properties of nimble addition, we can do this. T is equal to 0 nim sum T, and 0 is equal to S nim sum S nim sum T. And then we expand S and T. So S is equal to this, T is equal to this. And then we pair up all the piles that are not changed. X1 is paired up with X2. X1 is paired up with Y1. X2 is paired up with Y2. And because we know they are not changed, we can cancel them out according to this rule here, because X1 is the same as Y1, right? And everything cancels out except for this singular pile, except for this singular pair that is changed. And we know that this is not 0 because of this rule. So we know S is 0, and this is not 0. Therefore T must be non-zero as well. So this lemma is true. Now we have the second lemma. If the current nim sum of the game is non-zero, there is always a move that changes the nim sum to 0. So if we let S be the current nim sum of the game, and S is equal to all these piles nim sum together, we know that S can be represented as a series of distinct powers of 2, right? And if we let 2 to the power of k be the largest distinct power of 2 in S, we know that this power must have come from somewhere, must have come from one of these piles. And if we let AI be the pile that contains this largest distinct power of 2, we can conclude that AI nim sum S is always going to be smaller than AI. Because in this nim sum operation, 2 to the power of k will be cancelled out, because they both contain 2 to the power of k. So therefore, this changing AI to AI nim sum S is a legal move. And if we make this move, we will realize that we change the nim sum from this to this. So we change this part. And we then apply the associative property, and we take the S out, and then we get this is S, and we get S nim sum S, and that is 0. And there you go, that second lemma is proved. Now if we combine these two lemmas together, we get a winning strategy. To win a game of nim, always make a move that changes the nim sum to 0 by decreasing AI to AI nim sum S, where AI is the pile that contains the largest distinct power of 2 in the nim sum, and S is the nim sum of the game. What did this imply? So in our previous slide, where we analyzed the game using backward induction, we know that there are P positions and M positions, right? So this winning strategies only applies if you are presented with the M position. If you have to make a move on a P position, then this doesn't work. You can just make any move, and any move is going to be a losing move. So what this means is that there are unwinnable situations for the computers. So for example, this position here is an unwinnable position because the nim sum of this position is 0. And since it is 0, any move we make is going to change it to a non-zero nim sum, and that is a losing move for us. So I think this is a limitation of the game itself. So there will be situations in which our algorithm will always lose. It's not going to be able to win. For misery version of nim, the winning strategy is slightly different. The strategy is similar to normal nim, except for the situation where making a move will only leave piles of 1 stone. So if we look at this position here, all the other piles have only 1 stone, except for this large pile, except for this last pile. What will be the winning move here in this situation? And I think this is very immediately obvious because in misery version of the game, we try to make our opponent take the last stone, right? So we want to leave an odd number of stone. So instead of taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Instead of taking 12 stone from this pile and change the nim sum to 0, we take all the stone from this pile. And then we leave our opponent with an odd number of piles. And therefore, our opponent will be forced to take the last stone. So this is the only part of the strategy that is different in misery nim. Otherwise, all is the same. Now let's take a look at our code implementation. So I've broken my code into convert binary. What this does is that I look at the rock list and I convert each element to distinct powers of 2. So for example, this will be converted to this. Find best row. This function looks at the binary list and determine which row contains the largest power of 2 in nim sum. Generate board. Just distribute randomly generate an odd number of stone and distribute them among all the piles. Visualize board. Visualize the board by representing each stone with 0. Run normal game. it implement the winning strategy for normal play. Run misery nim. It implement the winning strategy for misery nim. Now let us run the code. Whoops, looks like it's a little bit broken. Okay. So let's just change this to 215 first. Okay. So we're gonna play normal. So for the purpose of demonstrating that my algorithm is able to play perfectly, I'm gonna just deliberately make a wrong move. This is not the correct move here because it leaves the nim sum. It doesn't change the nim sum to 0, and this is a losing move. This is a losing move here. But my algorithm, however, is able to make the winning move by changing the nim sum to 0. And then we're just gonna keep making losing move, and the algorithm is gonna keep making winning move. Indeed, in fact, there are no winning moves available to us now because the nim sum of the game is 0, and any move we make here is going to change the nim sum to non-zero, and it's always going to be losing for us. 3, 4. There's only one pile left. The computer take all the stones, and he wins. Now let us try the misery version, which has a slightly different rule set. We're gonna make a random move, which is a losing move, and then we're gonna keep playing. And at this point, we only have one stone left, and we're forced to take this stone. And we lost. The computer beat us again. It is, however, possible to win if you play perfectly. I will demonstrate this. We'll have to calculate the nim sum of the game here. So 4, 2, that is 4. So the winning move would be taking one stone from pile 1. And that changes the nim sum to 0. And now the computer is forced to make a losing move. The nim sum is 3 after the computer's turn. So now let's try to figure out what the winning move is. Taking one stone from pile 1 again. Now the computer is just making random move because it doesn't matter. Whatever move the computer makes is a losing move. We're gonna keep just normal. Yeah, so normal. So the winning move here would be 3, 3, and the computer is forced to take just one stone, and we beat the computer. So there are other popular algorithms for combinatorial games, such as the min-max algorithm and alpha-beta pruning algorithm. So what these algorithms do is that they assign a value to the game state, and it assumes that both players play perfectly. So the player, we should always try to maximize the value of our position, whereas our opponent should always try to minimize the value of our position. And it tries to search through the entire game tree and look for the optimal move. However, this is not really applicable, these type of algorithm, to the game of NIM, because the game of NIM is again an impartial game, and every position is either winning or losing. There's simply no point to assign a value to assign a value to the game state in an impartial game, because it's either 1 or 0. It's either winning or it's losing. And there's no point to search through the entire game tree either, because we can easily find the winning move by applying these strategies. So what is the impact of pile number and stone number on our algorithm? It might slow down the algorithm. However, the algorithm does have a time complexity of big O of n, because what it does is that it uses a for loop to search through all the piles. So it will be time complexity of linear. So realistically, there is no impact for the algorithm. So for example, if we try to play the game with, say, 100 pile, which is very large. Whoops. 100. What? seems that Anaconda is a little bit broken again. This program. This is frustrating. Okay. Oh. Let's comment this. I have to run over the cells. So here we try to generate a game of 100 pile, and we will remove from pile 100 3 stone. And now the computer is able to instantly find a solution, even though there are 100 piles. So realistically, pile number doesn't really have a impact on our algorithm. It does, however, make the game harder for humans to play, because it's going to take me an insane amount of time to try to find the nim sum of the game here. But for the computer, it's really easy. And then here are the references that I use for my project. And yes, thanks for listening.